We are live. Welcome, everyone. Nice to see you, Freedom. I'll give it a moment just to let everyone come in there. Thank you for waiting patiently. I see we had a few of you in the waiting room today. It's nice to see everyone back. Alexander, do let us know in the chat where you're watching from today. It's always nice to see. And some new faces as well. Good to see you all. Nice to see you all. Do say hi in the chat. It's let us know what the weather is like where you are. It's a very, very cold English winter here at the moment, very frosty. Nice to see you, Freedom. So just as a quick reminder, you can put any questions or comments into the chat while we go through this webinar. We will go to the Q&A at the end of the session, but I will try and get through all of the questions and comments that I can at the end. And this session is being recorded and will be available on demand. You'll be notified of that once the recording is available via email, and it will be on the network on our website. So in the interest of time, I will make a start. So with me today, I have Bibraj, who's a scientist and head of IT and X-band radar division for the Regional Meteorological Center in Chennai in India for the India Meteorological Department. And today he'll be discussing with us probabilistic nowcasting with auto alerting over Chennai, India using weather radar. So Bibraj, would you like to start for me?
Yes, Katie. First of all, I should thank Verizion Network for giving this opportunity to present our work in this forum. So I'll just share my slide. I hope it's visible to all.
Looks great. Thank you.
Yeah, great. So I'll be talking about the probabilistic nowcasting with auto alerting, which we had done over the city of Chennai, India. So before going into the complete system of how we are doing it, I just wanted to give a brief about how nowcasting is currently done in IMD. So we do have forecasting officers who actually look at different guidance. For example, the severe weather guidance from the National Weather Forecasting Center. And then they look at the satellite images, radar images, and the current weather observations, lightnings, and then some nowcast products, mesoscale systems, mesoscale products. And after that, they actually determine the kind of intensity of rainfall or any severe weather event which is occurring. And they identify the regions where this is going to occur. And based on that, they actually prepare a bulletin. That in that bulletin, they just give what kind of category color matrix it is, whether it is a yellow alert or orange alert or red alert in the increasing order of severity. And after the bulletin is prepared, they actually send it to different stakeholders, disaster managers, and the public through email or social media and all other different things. So this is how it is operationally currently done in IMD. This nowcast warnings are usually done every 3 hours. So every 3 hours, a forecaster would be actually looking at all these data and giving you the nowcast. If you look at the typical time period of how much time it takes for a forecaster to prepare this and actually to disseminate, it varies between 20 to 30 minutes because they have to do all these analysis, do the preparation, and do the dissemination. And you can, as you can see in the right, I'm just showing you here that we have the map which shows the radar coverage over India. So in this, I have also shown the proposed DWRs, the available DWRs, and different category like single pole or dual pole. Wherever a radar is present, what we have observed is when we observe these forecasters, whenever a radar is covering their particular location, their primary tool for nowcast warning is radar because it gives you the three-dimensional structure of the weather there, weather in the sense the precipitation and cloud and things, and it has a high spatial and temporal resolution. So they prefer this Doppler weather radar. And going ahead, looking at the map, very soon, within a couple of years, we would be actually covering the entire India with radar, and it would be the primary tool for nowcasting for all the people out there. Now, coming to that, the next thing would be the spatial domain in which we are actually giving the forecast or the nowcast. You can see here the left hand side part of where I'm pointing out here. This is the map of India, and you can see the broad lines, the dark lines, black lines. These represent actually different states. So usually a weather forecasting office is located in a particular state. There are 28 states in India, and there are weather forecasting offices located in each sites. And if you look at, just zoom into that particular state, you see this here where I'm in the middle of the slide. This is actually a state and a weather forecaster actually issues this nowcast warnings for this whole state. Now, the whole process, as I told, of identifying and giving this color coding applies to this domain for each particular state. They used to give different color coding. Now, if you look at the spatial area of these district, with what we call as district level warning, some districts are as big as 2,000 square kilometers, and it goes even up to 7,000 square kilometers. So that is the range we are talking about. So they used to issue warnings for this every 3 hours. Uh, Now, when looking at this, what are the challenges? What we face here is basically you can see that the warnings are given once in 3 hours, and the spatial domain is also larger. Now, if you come to cities, where mega cities as we call it, in these urban places, people actually expect hyper local forecast or nowcast. Like they want to know exactly whether it will rain in my particular location, not in a very larger domain. But having said this, there is a challenge from the forecasting desk where within this 3 hours, they are actually looking at 38 districts. If you see this operational system here, one state actually has 38 districts and it varies between different states. So a forecaster has to look at all these 38 districts and then they have to give forecast. This is really challenging. And it is even going to be even more challenging if we ask them to tell, if we ask them to actually give nowcast for even higher resolution, like, say there are nearly 300 taluks or, a higher resolution domain within this one state. So it may not be possible for a single forecaster to give that. So what we thought was, you can see this particular area where I have highlighted, and that is actually represented here in this as a taluk level, which I'm giving like it's an experimental nowcast, which I'll be discussing in today's presentation. You can see this only this small area can be even subdivided based on administrative kind of categories or administrative boundaries. Here you have the spatial domain anywhere between 10 to 100 square kilometers, less than 100 square kilometer each blocks. Now, to give this kind of nowcast from the forecasting desk is definitely going to be challenging. So our idea was, is there a possibility where we can automate it, or we can have a nowcast system where we can able to generate nowcast at this high hyper local resolution. And also considering, like, it also happens that a forecaster, though the SOP says that the nowcast bulletins are issued every 3 hours, and in between if any activity occurs, you can still, there is no restriction on giving a new alert. But usually due to the workload of this forecasters, what happens is they tend to stick to that once in every 3 hours. So there are chances the formation or new alerts which can be generated within this period are missed, or any new development of precipitation is missed. So considering all these things, we thought of having a model or a system where we are trying to actually do what a forecaster is doing automatically. So the input here, we were thinking about the radar data, which is having a very good resolution. And then we are putting it to a nowcast module, which is going to tell us like what is going to be the precipitation in the next 2 hours in different particular regions. And then we'll be generating some auto alerts and then we disseminate it. Now, though it looks quite simple in the way it is put out, there were a lot of challenges. The first challenge when it comes to the radar data was the preparation of the radar data sets. So The thing is, like, we did not purchase all our radars at one go. It was during different phases of the development of meteorological services in the country. So each radar had a different kind of manufacturer, different kind of data format. So we had to standardize it, and then we had to do quality control. These were one of the aspect of it. Then we need to identify a reliable nowcast module. Now, when I say reliable, I am not telling like it should be 100% accurate. No, it cannot be possible. Like, you have a 100% accurate system, but it should be reliable for us to say, okay, it can be done automatically. We can trust this, that we can go with the auto alerting system, and then we had to design an algorithm for this auto alerting, which is foolproof. So these were the scientific and technical aspects of this particular work. And then we were thinking about the operational issues. Like, for example, we were using some Nowcast products earlier also, but we had some challenges, like, having to purchase some Nowcast products from certain companies. What has happened is, it has a high initial cost, it has a high maintenance cost as well. And whenever we need to make a change, or we need to make an improvement, or when we need to go for an upgrade, it becomes a challenge because everything has a cost. So there will be additional cost for upgradation. So it was making things difficult for us. It was rigid. So the first decision we took was, within a lot of open source libraries available, we should be selecting a Nowcast module which is actually open source. And the second one was it should be easy to scale and deploy, because India is a very large country, and we need to install this at different stations. And for that, it should not be very complicated to install and things like that. It should be very simple. And the third one was minimal computing time. This was a very crucial requirement which we had, because whenever we are going to buy bigger systems, it has a higher capital cost, and we have to do an annual maintenance charge for that. We have to maintain it, we have to change the space. So we thought, we should not have a specific high level computing system to do it. It should be in a normal workstation, which is, part of any office. So it should be able to, we should be able to do that in a very normal workstation. So that was one of the things which we had in mind for developing that. And then coming to the third part, that is the dissemination side, we were thinking about highly localized forecast. Now, when we say, like, we are going for automation, we are going for AI, usually the forecasting people, they think like, you're trying to take my job away. I'm doing something and you're saying computer will do it. So we are very conscious that, see, we are not entering into the domain which you're already doing. We are not going to get into the district forecasting level, because that's already being done by you. We are going to do something in a much more hyper local, which is not possible for a human to do it on that much scale, like, 300 taluks and this thing. So we had demarcated things very clearly for this. And then we thought, no, we should do a reasonable lead time for any warning to come up. And the warning should not be simply text based, it should be graphical to, catch the attention of the users. And our primary target was the social media, because that is where everything is happening right now. And people are constantly on the phone, and that's where you get the nowcast very fast to them. So considering all these things, we first experimented that in Chennai. So just a brief about the city of Chennai. The city of Chennai is located in the south of India, and it is in the Bay of Bengal coast. It's a part of the state of the Tamil Nadu. The annual rainfall is around 140 to 140 centimeters. And the thing is, like, almost 50% of this rainfall is during this October, November, December, like, the current period what we have. And it is caused by synoptic systems, like it could be a low pressure, and then we have depression or cyclone. So most of the rainfall is based on these kind of synoptic systems which develop in the Bay of Bengal. So usually what happens is you'll have episodes of rain for probably 3-4 days, and then you have a lull period, and then again you have some rainfall. I was just discussing right now, like, currently we are in a lull period. We're expecting a cyclogenesis in a couple of days, and I'll be busy in the next week. But luckily, it was in a lull period. So that's how the rainfall occurs in this particular region. The city has a population of around 12 million people. India is a populous country, so obviously, our cities are very crowded, and a lot of the population density is very high. One of the major concerns is the urban flooding. There's a lot of inundation which occurs in low-level areas. Even in the recent rainfall, the people actually took the cars from, because they're living in the low-lying area, they took their cars and they parked it on top of the bridges to, so that they can safeguard their car. Because I think the last year when we had given the flood warning, but still when people had kept their cars in their houses, it was flooded and the insurance costs were too high. The turnaround period of cars were so high. So now people are more aware and they were, just parking on the bridges so that it is not affected by flood. Now, having given a background of the city of Chennai, and just also including, there are two radars there. One is the S-band single polarization radar and the X-band dual polarization radar, which covers the city, and they are actually 17 kilometers apart. Now, this is where these two radars are located at. The S-band radar is manufactured by Selex, and it has a frequency of 2.87 gigahertz with a range resolution of 150 meters and beam width of 1 degree. We have two scans. The short scan, which is a volumetric scan. A volumetric scan means actually it looks up to 10 elevations. It gets a complete picture of a 3D picture. That runs for 250 kilometers. And we have a long range scan. We call it as a surveillance scan. In X-band, it was manufactured by MS Data Patterns. It's a local company here in India, and the frequency is 9.3 to 9.6. The resolution is 150 meters, beam width of 1 degree. Of course, the people who are familiar with radar will be knowing that the attenuation of X-band is much higher than S-band. So the scan is limited to 85 kilometers. The long range scan is just a surveillance scan, but our main concern is about the 85 kilometers. The temporal resolution, that is like we get data every 10 minutes, and the number of elevation angles is 10. And having said that, now this is what I've talked about is radar. And next, I was coming to this open source nowcast model you're talking about. PySteps is the nowcast model which you're using, which is an open source framework for probabilistic nowcasting, which anybody can use. It's available for free. And this any nowcast model, any extrapolation based nowcast model has two parts. The one part is we know currently where the clouds are located, where the system is located, and we are going to extrapolate it and tell, like, next 2 hours where this cloud is going to move. This is one part of the problem. The second part of the problem is as it moves to the new location, how it evolves, whether it gets strengthened or whether it is going to get weakened, and that is the second part of the problem. Now, what this nowcast module does is, it has one part where it has the Lagrangian persistence that is moving the system from one location to other. The second one is, since we are not using any NWP modeling here, it's only a extrapolation based nowcast. It introduces some random perturbations which simulate how this cloud is going to behave. So, but the simulation may create a bias. So what we are doing is, like, there are a number of ensembles, like, right? There are a lot of ensembles. So this ensemble will give you a probability, or it will reduce the bias. So the final output is basically a combination of these two both. One is the deterministic part, and second one is the random perturbation part, which is kind of modeled to kind of identify the evolution of the system, like temporally, whether it will be strengthened or it will be weakened. So based on this, we found, the papers, it was a very good model. We thought we want to test it out. Now, the initial hiccup was there are certain file format which is being supported, and you can see that most of the uh, radar data is supported, which is being used in the developed countries. And with respect to the IMD network, we have, as I told you, the development happened in space in different time periods. So we had radars from different manufacturers. Like, we had Celex, we had Vaisala, we have Data Patterns, we had Bell. So what the first requirement was to write some functions which will actually be able to read this data, making it compatible with the nowcast module. So we can see this the 3-4 programs which we have written, which will actually uh, make our radar IMD's radar data compatible with this module, nowcast module. Now, when it comes to the input data, like what are the data we are using? For example, if you take the S-band radar, we take a 1.5 kilometer CAPI. The CAPI is constant altitude plant position indicator. It means like we are taking the reflectivity at exactly 1.5 kilometer above from the ground. And then we're using a ZR relationship, which is 267 and 1.345. The reason we are taking this is based on our previous literature, like research studies which have been undertaken in Chennai. Based on that, we have used it. For the S-band radar, the KP product data quality is good. So hence, currently we are using this S-band radar data. The X-band radar, there is no inbuilt CAPI which is being generated. So we are actually generating a gridded data based on PyArt, which is again an open source software which is available. And then we are converting it into rainfall. The challenges here is the S-band, though the data quality is good, it's a single polarization radar. So you do have challenges in getting a very accurate rainfall estimation. When it comes to X-band radar, yes, it gives a good rainfall estimation, but unfortunately in our case, the KDP product and the rainfall derived products are not readily available. So this is something which we need to generate based on the available resources in open source forum, and we have generated it, and we are in the process of validating whether this could be used for this particular application. Now, this is just a snapshot which I'm just showing to you regarding this tropical cyclone Mandus, December 2022. The left-hand side of what you're seeing is the actual observed precipitation or the precipitation caused by this Mandus for a 2-hour period. You can see here it is just changing from 0 to 120 minutes. But this is the actual observed precipitation. And what you're seeing in the right is the nowcast precipitation 2 hours before. So this is not taken every 10 minutes or something. This is 2 hours before. It is capturing how the precipitation fields are moving. You can see the actual movement of the precipitation fields are very well captured here. The rainfall here and this particular region is also very well captured here. But one thing is missing. You can see that the areas where new clouds are forming, you can see here there, we see new precipitation cells forming, which is not captured by this. So the thing is, like, one advantage is like we are not running the system every 2 hours. We are running it every 10 minutes. So I just for showing you how good it is in the 2-hour period, I've just shown you this. But since we are generating every 10 minutes and we are checking whether any changes is taking place, so we had not much to worry about this, because even if new cells were actually coming up in the next scan, it will be captured in the next 10-minute scan. So it did really well when it came to a forecast. So this is an example, how this these you can see here, this B, D, and F are actually observed precipitation at 30 minutes, 60 minutes, and 120 minutes. And the below one you can see are the nowcasted actually precipitation in 30 minute and 60 minute and 120 minute. It more or less matches. One thing we can observe here is the areas where the rainfall is going to happen, that is captured pretty much well. The problem would be in the intensity, like, whether it is being in the heavy rainfall category or something, it's going to change. For example, here you can see in the diagram F, you can see the intensity is pretty high, but in the nowcast, it is not being captured quite well. But again, this is a 2-hour period, what we are talking about. Now, then, see, this is the science part of it, whatever I said, and then we had to fine tune it, to our system. So I'm just sharing my experience, like how we are doing it, and maybe if somebody's trying to attempt it, this might help them to carry it out. So we analyze the optical flow method. So what is this optical flow method? This is the algorithm which actually is used for predicting how the cloud will move based on the previous images. Like knowing, like, you're walking in a straight line and I have been observing it, so you'll assume that it is going to go in a straight line, right? So similarly, by looking at the pictures in the past 1 hour or 30 minutes, it's going to tell you, like, next 30 minutes where these clouds are going to move. So there were actually three major optical flow algorithms in the framework. One is DARTS, which uses a spectral approach to find the sequence of radar fields. The one thing in the radars, the important thing is it requires a longer sequence of radars to do this prediction, like six pictures are required. Considering our 10-minute scale, it requires at least 1 hour of past data to predict it. Otherwise, it may not be able to predict it. Then we have the variational echo tracking algorithm, which is actually a global optimization routine, which minimizes the cost function between the displays and referent image. Based on that, it will be telling you how the cloud is going to move. And third one is a very famous and something which is widely used in computational or image processing areas. That is the Lucas Canade method. In this Lucas Canade method, we use two or more radar images and then interpolate to find out how the cloud is moving. This uses past 30 minutes data or something like that. And then we did an assessment, because when you're going for auto alerting, you need to look into all the aspects, like whether it is good for stratiform precipitation, whether it is good for storms, whether it is good for convective activity. We need to look into all those stuff. And also, as I told you, we had some operational issues of computing time and all those stuff. Now, when we actually checked it out, you have the fractional skill score. 0 means the very poor skill score, and 1 means the best skill score, right? So we did for stratiform, we did for convective, and we did for combined. And what we understood was there was no very significant difference. Of course, you can see in the chart here, there is difference. There's no denying it. But we didn't think like it was significant enough to make a very to say yes, yeah, this is the best one. No, it was not that much different. There was a variation in it. So we looked at the computing time. When we looked at the computing time, the Lucas Canade took only 2 seconds for generating this optical flow, and the DARTs took 5 seconds, and VET algorithm took 38 seconds. Since we had to reduce our computing time and there was no significant difference in the performance, we shortlisted Lucas Canade and DARTs. And in this, the problem, I won't say it's a problem. The requirement of DARTs was like you should have at least 1 hour of past data to generate it. Now, for a city like Chennai, the network is good. We won't have any issues in data coming and processing and things like that. But if you're going to expand it to remote places where the radar is located, there may be issues like a single radar data might be missed in the transmission, the networking stuff. So what happens is the model will not run for next 1 hour, because it has to wait for at least past 1 hour data. So even if one data is missed, we'll not be able to generate any output for the past 1 hour. But Lucas Canade will run even with 2 images. So even if a data is missed, you will anyway get a data within half an hour. So considering all these things, we thought, okay, Lucas Canade would be best suited for us. This is only on the operational front, because see, we are an operational department. We are analyzing on all the aspects before actually going to the public. And then, as I told you, the ensembles, number of ensembles is going to tell you how good it is. So we had put different ensembles, 24, 48, and 72 when we tested it. With respect to the stratiform precipitation, there was absolutely no difference at all. It was almost same. There was no improvement in the, the skill score. But when you looked at convective systems, it was slightly better, and that too only for the first 60 minutes. After that, it was all merging towards the same skill score. But in the initial 60 minutes, the 48 and 72 ensemble was better. Now we had thought about it whether we need to go for a 48 and 72, and then we thought it's only a slightly better this thing. In our current requirement, like we are giving us very subjective auto nowcasting, we thought no, we'll stick to the 24. One of the primary reasons for sticking it to it is the computing time. If you look at the computing time in the third chart, you can see here that for the 24 ensemble, it took 95 seconds. For 48, it took 191 seconds. And for 72 ensembles, it took 289 seconds. This is only for ensemble prediction, only for that computing part. Again, you have the dissemination part, which takes some time. And we already saw the optical flow part, which takes some time. So this is only about the ensemble part. Now, considering this, we thought, we did the trade-off. We'll say, okay, for our systems, like, mostly depression-based system, I think it should work fine. We may not have that much issue. So we thought, we'll stick to the 24 ensembles. We want to save the computing time and the performance. So we stuck to that. and we selected a 24 ensemble model. And then after all these things, we also need, once we decided this, we just thought like, let's go and actually run it and see how the skill scores are. So we took different days. I'm just giving you some examples, not the entire data set. So on, let's say on 5th October 2022, there was a combination of stratiform as well as convective storms. So in this particular day, we saw that the maximum skill score was around 0.62, an average skill score of 0.30 for the 2 hour period. So, and when we actually looked at the individual samples, we understood that the higher maximum skill score was due to the stratiform precipitation. It was not due to the convective precipitation. The convective precipitation was actually bringing down the skill score of the system. And then we thought we'll go only for the convective system. This convective system on this particular day, all these terms actually had a very short lifespan. Like, they were just alive for, 30 minutes or, 45 minutes, and everything was only few storms actually lived up to 60 minutes. So we can see like it has very poor performance in the two hour period, because it is a extrapolation based nowcast system. And we very well know that it may not be able to predict the genesis of new storms. If there is already a storm, it can try to evaluate whether it is going to get strengthened or weakened or how it is going to move. But if there is no system available or there's no storm, it is not going to tell you like at this particular place a storm is going to pop up. So we decided, okay, this is not going to be part of this. Is this kind of storms would not be captured this particular model. And we did try it for different timelines also on convective storms, and we understood that yes, and we confirmed that it was continuously in the performance was poor when we had the convective system. But then we tested a different scenario where you have a convective storm, but those are not isolated storms. They are a bigger convective storm, because the spatial area of this convective storms was much larger than the isolated stuff. And what we saw was, the scores are they're not great, but it is much better than a isolated convective storm. It is around 0.4 for 2 hour period. And even if you look at a 1 hour period, it was reasonably good. So this made us understand that, it's not about whether it is convective or this thing. It's about like how large the storm is, it is able to predict better. So it is about the spatial coverage of the storms. And of course, we tried with stratiform, and it gave a very good performance. It has 0.78 was a maximum skill score for 2 hour period with the average score of 0.50. Even that was the reduction in mean skill score was due to some reorganization of the precipitation cells which happened, and that was causing a reduction in the skill score. For the tropical storm, it was the best, because tropical storms, the clouds are spread over a very large area and they are moving at a reasonable speed. They don't make any fast changes in the sense like, when the storm is actually in the sea and it is sending bands of clouds to the coast. It's pretty much, you don't see kind of random things happening here. You get a widespread rain and a good coverage. So we saw that the maximum skill score was very good. Now on an operational perspective, we did uh, 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 an identification. What is the critical skill score? What is the probability of detection? This was very important because, see, we are going to build a system which has no human intervention. So it is going to be purely automatic, and we need to understand each and everything of it, like whether it works, why it will work, why it won't work, so that we can understand where we are not correct and we'll try to correct it, or we can make changes to it. So that was the goal here. And here you can see for tropical storm, it is good. It's very good. And next comes the stratiform, and then the last is convective. So when it comes to probability of detection, you can see this is a very interesting fact here, that after 60 minutes, you see almost the convective and stratiform merges together. So this gave an idea like, it's not basically about the convective or stratiform that is at role here. It is basically how long the storm is going to stay and how big it is. that is going to determine how good the nowcast model is. So if a system is bigger and is going to stay for a long time, definitely the model is going to predict better. But what we understood here is when we are going for an auto nowcasting, we should keep a threshold for alerting. And that is going to be a problem when we are going for a deterministic nowcast, because it is going to differ, the accuracy is going to differ for each and every precipitation. For tropical storm, it is going to be different. And this kind of inconsistency may affect like how the people perceive the utility of this nowcast. So considering all that, then we thought like, we wanted to go with probabilistic, but we were going step by step. And after seeing this, we thought, okay, we'll try with the probabilistic nowcast. So this probabilistic nowcast actually gave us an extra parameter to play upon. That is the probability threshold, which was not there earlier. Earlier, it was only a deterministic probability. You just say whether it will rain or it will not rain. So based on that, you have to give an alert. Now we get an additional parameter because it's an ensemble model. We generate probability, like what is the probability of light rain? What is the probability of moderate rain? What is the probability of heavy rain? And it gives you a lot of values of probability: low probability, medium, high, very high. And when you look at the statistics, when you look at the skill score, for example, I'll just show you the skill score. Uh, this is the skill score which you're talking about. In the left hand side, what you see is a stratus precipitation, and you can see this curves here. This is the 30-minute, 60-minute, 90-minute, 120-minute. So if you, let's say I'm selecting a probability of 10%. Okay, so I decide that whenever there is a probability of rainfall more than 10%, you give an alert. In that case, I can easily determine that my POD would be 0.9 and my false alarm would be 0.2. And for this is a convective storm. Here, if I'm going to give a 10% probability, then my POD would be 0.8, but my false alarm will exceed 0.2. So this probability nowcast actually gave us a tool of which probability should I select to maintain a maintain some X or Y number of probability of detection and false alarm rate. I hope you were able to get what I'm saying. Like it gave us a tool actually to decide what false alarm rate we want, what is the probability of detection we want. Now this actually helped us a lot to find out like which should be the correct thresholds to keep. Now for the auto alerting, we took a decision that we don't want false alarms because once people think it's a false alarm, there's a good chance like people don't believe this forecast. um, Even if we lose on probability of detection, it is okay. Even if we miss something, it is okay. Why? Because we have district warning already available. Already, the forecasters are issuing district warning, which is going to anyway cover the overall picture. We are just going into a hyper local forecast. So anyway, we are covered. We have the district forecast, which is covering this area anyway. So when you are going for hyper local, let's focus on giving a forecast which is reliable. Like you have to, you can take action that if it's going to rain, it'll rain. We did not worry about probability of detection because every 10 minutes we are generating this product and it will be looking at the current live radar data also. So only thing is it is not going to miss any kind of precipitation. Only thing is your lead time only will be affected. Sometimes, you are you are trying to reduce your probability rate, and what happens is it next 1 hour it won't be showing. But since you are checking every 10 minutes, immediately if the cloud is seen in the radar, it will give an alert. Of course, the lead time is affected, but still the POD and the false alarm rate is within this range. So we had considered this and we thought, okay, this is good to go. And we actually summarized the highlights of the study. Like, we did it for more than 750 samples with different precipitation types. We understood that, for widespread precipitation, which is persisting for a longer period, it works very good, and that is the kind of precipitation which is prevalent over Indian region for southwest monsoon, northeast monsoon, and also during tropical cyclones in summer. Only the convective storms during summer and other period we'll be missing. We will not be able to find it because the skill score is very poor for systems which are short-lived and a very rapid change in storm dynamics. And we also understood that probabilistic nowcast is best suited for the alerting because the probability variable can be tuned for reasonable accuracy. So basically what we are trying to say here is whenever we expect there will be a lot of stratiform kind of precipitation, we keep our probability low in the sense like, we keep it like into 10 percentage or 50 percentage. So we keep the probability threshold as 50 percentage. Even there is a 50 percentage chance of rainfall, it will give an alert. So it works good because even for 2 hours we saw, we get a reasonable POD. But if it's a convective storm, then what we used to do is we used to increase the probability of detection. I mean the alerting threshold to 90 percentage. So it's like only if you're 90 percentage sure it will rain, only you give that because it's a convective storm. We know the system is not going to perform better. So we have kept a very high probability threshold to generate an alert. Now, this is a flow chart of how we are working out this. So basically, you get this radar data, gridded radar data. It goes to the PySteps nowcast module, and it generates the precipitation nowcast for the next 2 hours. And then first we check whether there is any precipitation. First check is whether there is any precipitation for a region. Like so, whatever I showed you in that picture, we have 41 taluks is around 6,000 square kilometer area. So each taluk, each district will be checked whether there is any precipitation nowcast in there, and then it will see what is the degree of precipitation, whether it is high. If it is high, the next thing we'll check is whether it has crossed the probability. I mean, like if it is more than 50 or 60% of probability that there will be heavy rainfall, and then it will be added to a list where we say that this particular area or a taluk will be getting a heavy rainfall. And then if there is no heavy rainfall probability, only then it will be coming and checking whether there is a moderate rainfall probability. And again, we have a probability threshold for moderate alert, and then we have for light rain. So it's a sequence. So if a taluk is already declared that it is going to get heavy rainfall, then we don't actually check for light rainfall because we are already giving the highest alert for that particular region. So we need not again give a lower alert. So once all these regions are scanned or identified and the list is prepared, then the alerts are generated and it is being disseminated directly to the public. So this was the basic flow chart of how this works. And every 10 minutes we are running it and it takes around 240 seconds. I'm telling the whole process from the data received to the dissemination, it takes 240 seconds. As I told you earlier, in a normal case, a forecaster manually to do it, he might be taking around 20 to 30 minutes, which is being done in actually 4 minutes for a even more hyper local area. So that was the idea which we were trying to implement it here. So this is the final auto alert, which this is in the X platform, currently X, earlier it was Twitter. You can see that the messages are generated in regional languages as well. And you can see the coloring, the graphical coloring, everything is automatic. It's nothing is done manually. It plots this thing and posts it directly in the uh, social media websites. It also sends an email to the disaster management on which location has this alerts. So we have been running it for the past, I think, 1 or 2 years. This thing has been going on experimental mode. What we subsequently observed is like, see, you can see here, we had separate alerts for light rain, we had separate for moderate rain, and we had separate for heavy rainfall. But this was actually flooding our timeline because every 10 minutes we are generating, it was repeatedly doing. Initially, people were, liking it and they were like saying great and things. But as time passed, people were thinking like, we are getting a lot of, things in our timeline. So we thought, we need to change it. So we had moved to a combined alert. Like now what we thought was in a single image, we'll put all the alerts instead of having a separate light, moderate and heavy. So we put in a single image, like giving different colorations to different areas, and you can see the post on the right, which will combine all these things, and it will post automatically in our X handle. We got a very good response for this. And another thing, what we did is, instead of running it every 10 minutes, we were running it once in an hour, because even generating every 10 minutes was actually, kind of flooding the timeline, and the important updates were not coming to the people. So what we thought was, we'll keep it once in an hour. So you can see here at 5:07 it is generated. The next one will be 6:07. So people will be waiting, like, okay, every hour I'll get an update where it is raining, where it is going to rain, and make decisions accordingly. So we had changed it accordingly. And this also gave us one more advantage, that in a single system, you can go up to 6 or 7 radars. Earlier, we had one machine for one radar, but we thought, since, we are not running it for complete every 10 minutes, so the running is going to happen only once in 1 hour. So you had the complete window open. After the initial 4 minutes, remaining 56 minutes, the system was idle. So if you bring all the radar data into it, so we can just time multiplex it. So the first 5 minutes, it will be running for one radar data, next 5 minutes for other radar data. So we thought, we can run it like that. And yes, we got huge appreciation from the public. These are all comments what we got from the public, that it is great, and we had increased our followers substantially. The name Radcast is actually a local name which we keep. It's not a scientific thing. It's like, kind of a internal project name what we kept, and we got a very good appreciation for this. So coming to the last slide, talking about the future plans, we are going to modify the alerting mechanism as per the evolving preference of the public. As I told, we are constantly changing. Earlier, we had a different alerting for different category. Now we had combined that. And then, as I was telling, this probability threshold, we are doing it manually. We are changing it manually. So now we are planning to use AI to actually read all those things, and then it will suggest us which should be the best probabilistic threshold to keep, so that you get a lesser false alarm rate and a higher POD. And we are thinking about creation of an API from this output, so that if anybody's mobile, they can fetch this API, and based on the location of that particular user, whether it can identify which location he is in and what kind of alert he's going to get, and it will pop up in his mobile. Instead of the social media, we get into this API mode. And also the auto generation of this cap alerts. Like, now common alert protocol is something like which everybody is focusing on, because it is, it's universal. Once we put in the cap, we need not worry about the way in which it is disseminated, because once we put in the common header, it will be transferred to all the available dissemination services. So we are working on that. And also the improving the nowcast model to better capture the convective precipitation. That is still a problem, and we think like we need to work on that and improve it. And as I told you, the other issue, like having a single polarization radar, our QP estimate is not up to the mark. So that also we need to work it out. After maybe we fix this issues in the dual polarization radar, we would be able to get a better quantitative precipitation estimate. So thank you. Thanks for this opportunity.
Thank you very much, Bibraj. And thank you everyone for watching this webinar. If you are watching this on demand, I'm sure you can contact Bibraj there if you have any questions that you haven't had a chance to be answered here. I will open the floor for some questions now. So if we have any more, do pop them into the chat or the Q&A. The first question I will ask Bibraj is, are there any developments to incorporate machine learning or AI techniques into the system?
Yes, Katie. As I was telling, like, now we are actually setting what is the threshold for generating this auto alert. Like, for example, when we expect there is going to be, stratiform clouds, we know the system will perform better. So even if you're going to give a low probability, it is going to perform better. We know that. So what we do is we reduce the alert threshold to a lower level. But when we expect there are going to be convective, like in the summer season, so what we do in the summer season is, we know the precipitation is going to be only convective, and we know the system is not going to perform better. So what we do is we increase the probability threshold to the maximum, like 90%. So only if the model is 90% sure that there is going to be a rainfall, only then it will give. Now this part where we are doing it manually, we are thinking of feeding all these data to a machine learning model, which will tell us like which threshold you should use for different storm precipitation types. Like if in summer you use this threshold, for this kind of precipitation you use a different threshold. We think like probably AI will help us to give that a value. What would be the threshold?
That's good to know. And it seems like with the integration of AI into a lot of systems, that could possibly just learn even more and expand. I know you went into a bit of detail there near the end, focusing on the alerting that you're sending out to the public, which was fantastic. The way that you changed that to make sure that the vital messages were still getting through. The question here asks, are there any collaborations with urban planners or disaster management authorities to optimize the utility of nowcasting data?
Yes, we have a national level program called Sea Flows, which is actually a different team which is working on this urban flood management. So they are using the Mike model for giving this flood forecast to the city of Chennai. So we are not getting into the alerting part, but the nowcast outputs, which is actually a quantitative value, that output we are giving it to the Sea Flows. So they are integrating in their models to give flood warnings to the place in Chennai. So we are currently it is operational. We are sending them the data, and they are working they're integrated with the Mike model, and they are giving alerts based on that. So it is not the final alert which is going to them, but a thing before that. That is the actual output is going to them, because that will be much more useful for them than the final alert, which is more subjective in nature.
Excellent. Thank you very much. The next question asks, did you issue any nowcast alerts for windstorms, and how accurate were your windstorm observations using this system?
No, as of now, we have not gone into that particular. We are just sticking on to the precipitation nowcasting module. We are not getting into lightning or any other effects. For example, what you said was a very valid answer, like, a valid question that, windstorm is very important, especially in thunderstorms and things like that. We have, winds which are affecting our aviation and everything. But no, we are not doing it right now with this particular model. Only we are doing only for precipitation.
So thank you. Brandon asks, what kind of model inputs and domain sizes are used in Mike 21 that allows for nowcasting? Is it that you dedicate much computational resources to this, and how often are outputs produced?
I'm afraid like I may not be able to give any opinion on the Mike 21 part because I'm not involved in that. But I can tell you the output what we are giving to them from the radar is a geotiff file of the hourly precipitation data. That is what we are giving at a resolution of 500 meters and an area of 100 kilometers. That is the data which we are giving it in a geotiff format. But I'm really not will not be able to comment on how the Mike 21 model is used, because that is being done by a different team altogether.
Zach Kelly asks, would this be applicable for Africa, possibly?
Yeah, because the STEPS model was actually developed in UK. It is basically for UK, but we have adapted it to India since it's open source. And I don't think there will be any restriction in using it in Africa. It's open source, and you can definitely use it, this STEPS model. And with respect to the alerting, like, you can always seek our help, and we'd be happy to help you on that.
Excellent. That's good to know. So Zach Kelly, do feel free to reach out to Bibraj there. The next question I'll go to asks, what unique challenges does Chennai's geography and climate pose for nowcasting, and how does the system address these?
The major problem with respect to Chennai is, with recent terms, the heavy rainfall, heavy precipitation nowcasting is becoming a real challenge. Like, for example, even last month, we got 10 centimeter of rainfall within 30 minutes or something, in a very localized area. It was not widespread; it was very localized area, and suddenly the traffic and everything was going. And none of the models or none of the radar data was able to capture it early. I mean, of course, we were able to get the precipitation and things like that. I think now what we are doing here is a very subjective analysis. Like we are saying light rain, moderate, and heavy, which is a very subjective one. But or I would say it's a qualitative kind of forecast. But the real challenge, what you're asking is the quantitative part, like exactly how much it is going to rain, like in next 2 hours, like what would be the expected rainfall, and that is very important for these urban planners and flood management. And that is a real challenge, especially for a coastal city like Chennai, which it does not have which is almost as flat as the ocean. You don't have a place for all this flood to go and go. It is actually stay there for a very long time, and with all this urbanization, there is no and there's no space for actually the water to go down to the ground. So these are some of the issues which is actually affecting us. And of course, we have a problem with the weather forecasting also. It is not 100% accurate anywhere over the world. We still have those challenges. And that's challenges we still face in this Nowcast module also. We are trying to work upon it, like how to improve the accuracy.
Excellent. Brandon also asks, following the nowcast, are observations of precipitation assimilated into the next iteration of the nowcast?
Yes, every 10 minutes, we are taking the past precipitation, like half an hour data, and then we are generating a nowcast. But the nowcast output is not taken as an input for the next nowcast. Only the actual observations obtained from the radar for the past 30 minutes are used for the nowcasting. The nowcast output is not used for further nowcasting.
Good to know. Thank you. Do we have any further questions? Brandon would like to share his email with you, Bibraj. So I'm not sure if you can see it there in the messages, but I can email it over to you. He said, impressive work. Please take my contact. We have an interest in doing this, but for oceanic variables. And I think Brandon is working very hard at the moment on his own project. So I think that connection might be very interesting for you. So I can share that email address with you after
Sure.
the session if you like. Do we have any further questions at this point? I don't want to miss any, so I'll give you 30 seconds or so just to write some out. As I've mentioned, this is recorded. It will be available on demand. If you think of any questions that you wish you would have asked, do get in touch with Bibraj there. Hopefully this will be available within the next 24 hours, so you can watch it back. Do keep an eye out on some of our upcoming activities. We do have an event with the Pacific Climate Change Centre coming up in the next couple of weeks on innovations for climate solutions in the Pacific. That will be a virtual event, so do feel free to log into that and look at all the innovations we're showcasing with them. I cannot see any further questions, so I'll leave it there. Thank you everyone for joining us today, and thank you very much, Bibraj, for that really comprehensive overview. And hope to see you again soon, maybe.
Yeah, thank you. Thanks a lot for giving this opportunity. Thank you, Becky.
No problem. Thank you very much.
Thank you.